Welcome back to the deep dive. I want you to picture something with me for a second. All right. So let's say it's 3:00 p.m. You're at the office, you're hitting that afternoon slump, and you find yourself standing in front of the vending machine.
Ah, the great equalizer. We've all been there.
We've all been there. And you're staring through that slightly smudged glass. And there it is. On one side, you've got this perfect, glistening, chocolate-covered donut. It's just calling your name.
It's promising immediate happiness, a sugar rush, a rescue from the 3:00 p.m. blues.
Exactly. And then right next to it is a sad little bag of apple slices. You know, they look responsible.
They look like the right choice, the should choice.
Right, the should. And as you're standing there, it feels like this epic battle is happening inside your head. We always talk about it like there's an angel on one shoulder and a devil on the other.
The classic story. Emotion versus reason. The impulsive lizard brain fighting against your more evolved rational prefrontal cortex.
But the whole reason we're here today, the reason we've pulled together this incredible stack of research is because that story, it's just not right, is it?
It's not right. It's a nice narrative, but it's not what's actually happening. What's happening in your brain in that moment isn't a war. It's a math problem.
A math problem.
A very, very sophisticated and incredibly fast calculation. Your brain doesn't have a wants department and a shoulds department that are at war with each other. It has a single unified currency exchange.
And that is what we are digging into today. It's a February 5th, 2026, and this is our deep dive update on the neuroscience of value calculation. We're going to unpack how your brain takes two completely different things, like the sensory joy of a donut and the abstract concept of long-term health, and puts them on the same scale to make a choice.
And we're going way past that old limbic system versus frontal lobe model. We're looking at the specific brain regions that act as the accountants and the managers. We've got sources ranging from, the foundational papers back in 2009, all the way up to some really groundbreaking stuff from 2024 and even a couple from 2025 that are genuinely changing the textbooks.
It's fascinating stuff, because what this research suggests is that the same calculation your brain uses to pick a snack is also used to decide whether to help a friend or donate to charity. Altruism, it turns out, is also a math problem.
It is, which it takes some of the romance out of it, but it adds this whole other layer of just biological awe.
Okay, so let's start right there. This idea of a common neural currency. Why do we even need that? Why can't the brain just compare a donut and an apple directly?
Well, think about the kind of information each one represents. The donut is, it's a sensory reward, right? Taste, smell, the feeling of the sugar hitting your system. That's a direct physiological signal.
It's speaking the language of the body.
Exactly. But the apple, or rather the choice to eat the apple for health reasons, that's a conceptual reward. It's the idea of I will be healthier in the future, or I'll feel good about myself. It's an abstract, future-oriented signal.
They're speaking totally different languages. One is speaking sugar now, and the other is speaking future self-esteem.
Precisely. And it's not just two languages. What if the third option is saving your dollar? That's a financial language. What if a friend walks up and offers you a piece of their snack? That's a social language. For the brain to make any kind of rational choice between these things, it has to translate them all into one common tongue.
It needs to convert sugar, self-esteem, money, and social goodwill into, I don't know, let's call them brain bucks.
Brain bucks, I like that. Or neural utils, whatever you want to call it. It's a single common scale of value. The brain has to be able to say, this option is worth 80 points and that one is worth 65. Only then can a comparison actually happen. Without that, you'd be paralyzed.
You just stand in front of the vending machine forever because you couldn't compute the exchange rate between taste and virtue.
You literally couldn't.
Okay, so if we could shrink down and fly inside someone's brain at that exact moment, where are we going? Where is this currency exchange floor?
Well, the modern consensus, which is really solidified by a huge meta-analysis from back in 2014, this was Clitheroe and Rangel in Social, Cognitive, and Affective Neuroscience, they point to a core network, a kind of valuation triad.
The big three.
The big three. And the absolute center of it all, the one you really need to know, is the ventromedial prefrontal cortex, the VMPFC.
Okay, where is that, roughly?
If you put your finger right on the bridge of your nose, between your eyes, and go straight back into your brain about an inch or two deep, it's on the bottom middle surface of your frontal lobes. This is the head accountant. This is where the ledger is kept.
This is where all the different inputs get converted into brain bucks.
That's the idea. Then, working closely with it, you have the ventral striatum. This is a deeper, more ancient part of the brain. You often hear it called the reward center in the popular press.
Right, the part that lights up when you're about to get something you want. ooh, piece of candy feeling.
That's a pretty good summary, yes. It's heavily involved in anticipating reward. And the third, slightly less talked about member of the triad is the posterior cingulate cortex, or PCC, which is much further back in the brain. It's involved in memory and thinking about the self, so it likely helps provide context for these value judgments.
So you have the VMPFC as the accountant, the ventral striatum as the, I don't know, the eager intern excited about the reward.
And the PCC as maybe the historian, bringing up past experiences to inform the value.
Okay, but it's one thing to say these areas light up. How do we know they're actually creating a common currency? How do we know they're treating, say, a tasty snack and a financial bonus is the same way?
That is the absolute key question. And to answer it, you have to go back to a really foundational study. It's from 2009, so it's a bit of a classic now, but it set the stage for everything. It was by Fitzgerald, Seymour, and Dolan in the Journal of Neuroscience.
And they were tackling this apples and oranges problem directly.
Directly. They called it the problem of incommensurable goods, which just means things that can't be measured by the same standard. You know, how many compliments from a stranger are worth one really good cup of coffee?
A question I ask myself every morning.
So what they did was they put people in an MRI scanner and forced them to make choices between bundles of totally different things. You might be offered, say, a DVD and $20 versus a book and a promise of a future snack.
Just bizarre combinations.
Exactly. They were designed to be different categories of reward, and they were watching one specific part of this network, the orbitofrontal cortex, or OFC, which is really the most forward part of the VMPFC.
What did they see?
They found something incredible. They found that the activity in this brain region didn't track the items themselves. It didn't care if it was a book or money. It tracked the difference in subjective value between the two options.
Okay, break that down for me. What does that actually look like?
Imagine a neuron. Let's say you're offered option A and option B. If you slightly prefer A, this neuron might fire at, say, 10 times a second. But if you massively prefer A, it fires at 50 times a second. The firing rate was a direct readout of how much more do I want this?
So the neuron isn't a money neuron or a food neuron. It's a wanting neuron.
It's a wanting more neuron. It strips away the physical properties of the object and encodes only its pure, abstract desirability. That is a common currency. It's the conversion of the physical world into a signal that the brain can use for a simple mathematical comparison.
That's amazing. It's like it takes the t-shirtness out of the t-shirt and just leaves behind the value-ness.
Precisely. Without that process, choice as we know it would be impossible.
Now, something you said earlier about the ventral striatum, the reward center, has me thinking. We talk about value as if it's always about getting something pleasurable. But, I mean, sometimes we seek out information that we know is going to be painful.
Oh, absolutely.
Like, checking your bank account after a big weekend.
Yeah.
Or looking up the calorie count on the menu after you've ordered the cheesecake. You don't want to know, but you also have to know.
That is such a critical insight. We tend to conflate value and pleasure, but the brain treats them as separate things. Information itself has value, even if that information is negative.
So how does that work?
There was a really clever study on this by Philemon in 2020, published in PNAS. They wanted to tease apart the value of a reward from the value of just knowing about the reward.
Great.
And they looked at the ventral striatum. The old view was that this area only cared about good news, food, money, attractive faces, that sort of thing. But what Philemon's group showed is that its activity can actually dissociate the anticipation of information from the anticipation of the reward itself.
So my ventral striatum can get excited about finding out the answer, even if the answer is you failed the test.
Yes, the brain places a very high value on resolving uncertainty. Uncertainty is metabolically costly. It's stressful. Finding out the truth, good or bad, provides a kind of relief, and that relief is registered as a value signal. The knowing is a reward in itself.
That explains so much about human behavior. It explains doom scrolling, for instance.
It's a perfect example. You're scrolling through an endless feed of terrible news, you feel awful, but some part of your brain is getting these little pings of value from resolving the uncertainty of what's the next horrible headline. It's a powerful, powerful drive.
Okay, so we have the geography. We've got the VMPFC and his network turning the entire world into a single stock ticker of value. But knowing the values isn't the same as actually making the choice. I can know the donut is an 80 and the apple is a 60, but there's still that moment of hesitation, of back and forth. How does the brain go from valuation to decision?
So now we move from the where to the how. And this is where we have to talk about the dominant model for decision-making in neuroscience today. It's called the drift diffusion model, or DDM.
I've heard of this. It always makes me think of, like, a drunken sailor trying to walk a straight line.
That's not a bad way to think about it. Imagine a graph. In the middle, you have a starting point at 0. At the top of the graph, there's a boundary line that represents choose donut. At the bottom, there's another boundary for choose apple.
And my brain is the little dot starting at 0.
Exactly. And as time passes, milliseconds by milliseconds, your brain is accumulating evidence. It's a noisy process. You glance at the donut, you process the sugary glaze. That's a piece of evidence for the donut. The dot drifts up.
Okay.
Then a stray thought about your last dental visit pops into your head. That's evidence for the apple. The dot drifts down. You notice the donut is on sale, drifts up. You remember you want to be healthy, drifts down.
So it's this jagged, random-looking walk that's bouncing up and down between the two choices based on whatever my brain is sampling in that instant.
Correct. It's an accumulation of evidence over time. And the decision is made the instant that jagged line hits one of the boundaries. If it hits the top boundary first, boom, your motor cortex gets the signal and your hand reaches for the donut.
This model feels so much more psychologically real than a simple, I weighed the options and chose. It captures that feeling of vacillation.
It does. And what's really important here, and this is a major update for 2026, is how this model changes our idea of self-control.
Ah, yes, the old story. The story I learned in college was that the VMPFC was like the impulsive child screaming, I want the donut. And another brain region, the dorsolateral prefrontal cortex, or DLPFC, was the rational parent saying, no, we will have the apple.
The famous dual systems model, reason versus passion. It's a very compelling story, but it's probably wrong. A really important paper by Hutcherson and colleagues in 2022 in the journal eLife has really helped dismantle that idea.
So what's the new story? What is the DLPFC actually doing?
What Hutcherson's work suggests is that the DLPFC isn't an inhibitor. It's not a parent vetoing the child. It's just another voice contributing to the evidence accumulation. It's just processing a different kind of value.
What do you mean, a different kind?
Well, the value of the donut taste, sugar, is immediate and sensory. It's easy for the brain to process that evidence quickly. The dot starts drifting up fast. The value of the apple health is abstract and long-term. It's a harder calculation to make.
It's slower information.
It's slower information. The DLPFC is the region that holds on to those abstract rules, like being healthy is a good long-term goal. So its job is to feed that health evidence into the drift diffusion process. It's adding its own data points, pushing the dot downwards.
So the DLPFC isn't fighting the VMPFC. It's just handing it a different spreadsheet and saying, hey, make sure you factor these numbers in too.
That's the perfect analogy. It's not a battle of wills, it's a race of evidence accumulation. Whichever type of evidence, the fast sensory evidence or the slow abstract evidence, accumulates enough to hit its boundary first, wins.
That reframes so much for me. It means when I choose the donut, it's not that I'm weak or that my self-control failed. It might just be that I was distracted or tired, and I didn't give the slow, abstract evidence from my DLPFC enough time to accumulate.
It's an attentional and computational problem, not a moral one. The sensory evidence is loud and fast. The abstract evidence is quiet and slow. If you don't actively create the mental space to listen to that quiet evidence, the loud evidence will win every time.
There's another timing question here that I've always been curious about. Does my brain know what I want at the exact same moment that it knows how sure I am about that choice?
That's a great question. And no, it seems there are two separate steps. A 2020 study by Shapiro and Grafton in PLOS1 looked at the precise timing of signals within the VMPFC.
And what did they find? A sequence.
A very clear sequence. First, very early on, the VMPFC encodes the subjective value. It basically says, okay, the donut wins. The choice is made, the verdict is in. The verdict is in. But then, a few hundred milliseconds later, which is a huge amount of time, neurally speaking, a distinct signal emerges in the same area that encodes confidence. It's the brain doing a quick post-mortem on the decision, asking, how sure am I about that choice?
So it picks a winner, and then it looks at the photo finish to see if it was a blowout or a squeaker.
That's a great way of putting it. It suggests that our feeling of confidence isn't part of the choice itself, but a rapid metacognitive assessment of the choice we just made. It's the difference between I choose the donut and I choose the donut and I feel great about it.
Okay, this is all making sense. We have the VMPFC as the accountant, the DDM is the mechanism.
Yeah.
But now we have to get to what you called the biggest update in the field, the one that's forcing people to rewrite the textbooks.
Yes. We need to talk about the anterior cingulate cortex. The ACC.
The ACC. For as long as I can remember, this was known as the conflict monitor. The idea was if you're really torn between two difficult options, the ACC lights up like a Christmas tree. It's the, uh-oh, this is hard part of the brain.
That was the dogma. The theory was that the ACC was involved in the decision itself, specifically in weighing costs against benefits. This juice is great, but is it worth the effort I have to expend to get it? The ACC was supposedly the place where that trade-off was calculated.
Supposedly.
Supposedly. But a really, really elegant paper by Kai and Padoa-Siopa in 2021, published in eLife, just completely turned that idea on its head.
This is the famous monkey study, right?
It is, and the reason it was so clever was in how they defined cost. In most older studies, the cost of a reward was just making the monkey wait for it. But waiting isn't really effort.
No, waiting is just boring. Effort is actual work.
Exactly. So what Kai and Padoa-Siopa did was make the monkeys perform difficult eye movements, these rapid shifts of gaze called saccades, to earn their juice reward. Some saccades were easy, some were really physically taxing on their eye muscles. This allowed them to perfectly separate the value of the offer, the juice, from the cost of the action, the work.
And they were recording from single neurons in the ACC while the monkeys were making these choices.
Right. And here's the crucial part. If the old theory was correct, if the ACC is the decider weighing cost versus benefit, then its neurons should be active before the choice is made while the monkey is deliberating. Their firing rate should reflect the calculation of juice value minus effort cost.
And what did they find?
Nothing. The neurons were silent.
Silent.
During the offer and deliberation phase, the ACC neurons did not encode the value of the offers. They didn't care about the juice. They didn't care about the effort. They only became active after the monkey had made its choice.
So what were they encoding then?
They were encoding post-decision variables.
Oh.
Things like chosen value, how good is the juice I'm about to get, and chosen cost, how much work am I about to do?
This is a huge shift. That means the ACC isn't the architect designing the building. It's the foreman on the construction site who gets the blueprints after they're approved.
That's the perfect metaphor. The decision, the trade-off, is made elsewhere, almost certainly in the OFC-VM-PFC. That's what we call good space, the abstract comparison of the items. Once that decision is made, the VMPFC sends the order to the ACC.
And the ACC then translates that decision into a plan for the body, into action space.
Precisely. The ACC's job is to say, okay, team, the decision is to get the high-value juice. That's going to require a difficult eye movement, mobilize the necessary motor resources, let's get to work. It manages the implementation of the choice, it doesn't make it.
Has this finding been backed up by other work?
It has. There was a big review paper in the journal Brain in 2023 by Claris and colleagues that looked at all the conflicting evidence about the ACC. And they concluded that this new model makes the most sense. The ACC tracks things like difficulty and conflict, yes, but it does so in the service of action, downstream from the actual evaluation and choice, which happens in the VMPFC.
Wow, so all those years of calling it the cost-benefit calculator were a misinterpretation.
It was a very reasonable misinterpretation based on the data they had, but this more precise experiment showed its role is more about execution than deliberation.
Okay, I want to pivot now because this is where it gets really, really interesting for me. We've been talking about donuts and juice and money. These are all, cold or selfish values. But so much of human life is about warm values, social values, helping people, being fair, being kind.
The social dimension.
Right. So where does that happen? Does the brain have a separate morality module? Is there a special lobe for being a good person?
This is where the whole concept of a common currency becomes so powerful. And the answer, according to all the latest evidence, is a resounding no. There's no separate moral center.
Wait, really? Not at all.
The brain appears to use the exact same computational machinery to value giving $1 to charity as it does to value getting $1 for yourself. This is what some researchers are calling the extended common neural currency.
So you're telling me that when I decide to help my friend move on a Saturday, my brain is just running an equation that says value of maintaining friendship is greater than the cost of a sore back?
At a fundamental level, yes. A 2023 review by Messamaris, Levy, and Labouche in Frontiers in Neurology really synthesized this well. They showed how the VMPFC is incredibly flexible. It can take these uniquely human social inputs like a sense of fairness or empathy for someone's pain or the desire for a good reputation, and it converts them into the very same common currency, the same brain bucks as a slice of pizza.
But that implies something really profound and kind of scary. If being kind runs on the same hardware as being greedy, What happens when that hardware breaks?
And that is exactly where the most cutting edge and frankly unsettling research is focused. We have to talk about what happens in patients with brain damage, specifically lesions to the VMPFC.
Hmm.
There are two huge recent papers on this. One is Lockwood and Culler from 2024 in Nature Human Behavior.
I read that one. It was chilling.
It is. They looked at what they called pro-social motivation. They had healthy people and patients with VMPFC damage do a task where they had to squeeze a hand grip to earn money. Sometimes the money was for themselves, and sometimes it was for a stranger.
And what happened with the VMTFC patients?
When the money was for themselves, they were fine. They worked just as hard as healthy people. They weren't apathetic. They weren't lazy. They were perfectly motivated by self-interest.
But when the money was for someone else?
Their motivation completely collapsed. They just wouldn't work. It wasn't that they were actively malicious. It was that the motivation to help another person simply wasn't being generated.
It's like the concept of helping someone else just didn't compute for them. It couldn't be converted into a value signal that could drive their behavior.
That's exactly it. The paper concluded that the VMPFC is necessary for pro-social motivation. Without it, the welfare of others has a value of 0 on the brain's ledger. It's an input that the system can no longer process.
And there was another one from 2025 that took it even further, right? Into learning.
Yes, this was Guegan and colleagues in the journal Brain. They showed that these same patients couldn't even learn to be helpful. They did a task where the patients had to learn by trial and error, which of 2 symbols on a screen would give a monetary reward to another person.
So healthy people would quickly figure it out. Oh, the blue square makes the other person happy. I'll pick that one.
Right, because a healthy brain gets a little burst of intrinsic reward, that warm glow feeling from the act of helping. That reward signal reinforces the choice.
And impatience.
They never learned. They performed at chance. Because their brains never generated that warm glow value signal, there was no feedback to tell them which choice was the good one. They were, in effect, incapable of learning to be altruistic.
That is just. It completely reframes morality.
Love
I
it.
think of good and evil as these high-level, almost spiritual characteristics. But this suggests that being good is, at its core, a neurocomputation. It's the ability of your VMPFC to correctly calculate the value of a positive social outcome.
And if that calculator is broken, the behavior we call goodness simply evaporates. It demystifies it, but I agree, it also makes it seem more fragile. It's a specific biological function that can be lost.
And it's not just the physical structure, it's the chemistry.
Yeah.
This brings us to a 2024 paper by Batten and colleagues that, the methodology is just unbelievable.
Oh, this study is a game changer. Usually when we talk about neurotransmitters like dopamine and human decision-making, we're making an educated guess. We use fMRI, which measures blood flow, and we infer that where there's blood flow in the striatum, there's probably dopamine release.
It's an indirect measure.
A proxy. A very rough proxy. But what Batten's team did was record directly from the source. They worked with patients who were already undergoing surgery for Parkinson's disease, which involves implanting an electrode deep into the brain into a region called the substantia nigra.
The brain's main dopamine factory.
Exactly. And they used a very advanced technique to measure, in real time, the release of dopamine and serotonin second by second, while the awake patient was playing an economic game that involved fairness and reciprocity.
So they were literally watching the chemicals squirt out as the person decided whether to trust someone or share money.
That's essentially it. It's the first time it's ever been done in humans for social decision-making. And they found that the release of these chemicals wasn't just tracking, did I win money? They were specifically tracking the social context. Dopamine and serotonin levels changed based on whether an offer was fair or unfair, predictable or surprising.
So these neurotransmitters are the ink that the social value calculations are written in.
That's a beautiful way to put it. They're the modulators. They're the chemicals that tune the sensitivity of the valuation system. Maybe a burst of serotonin makes the fairness attribute way more heavily in the VMPFC's calculation.
Which has some really big implications we need to come back to. But first, I want to close the loop on this new brain map. We've got the VMPFC choosing, the ACC executing.
Yeah.
What about the old story of the cortex versus the lizard brain? The rider and the elephant.
The rider and the elephant, the idea that the striatum is this powerful, impulsive elephant and the prefrontal cortex is the tiny rider desperately trying to steer it.
Right, I want that cookie. Versus the cortex trying to pull on the reins and say, no, we're on a diet.
That top-down suppression model is very intuitive. But a 2023 paper by Gore and colleagues in Nature Neuroscience suggests the rider has a lot more control than we thought.
How so?
They looked at the direction of information flow between the OFCV and PFC and the striatum. The old model would predict that the striatum fires off these bottom-up I want signals, and the cortex then has to step in and suppress them.
Holding the beast in check.
But what they found was that the OFC is often the one leading the dance. It's sending top-down signals to the striatum to guide its activity. It's not just saying, don't pursue that donut. It's actively telling the striatum, hey, that apple over there, that aligns with our current goals. Assign a high value to that and go get it.
So it's not just a brake. It's a steering wheel. It's top-down guidance, not just top-down suppression.
Exactly. It suggests our conscious, goal-directed cortical systems are much more in the driver's seat of our motivational systems than the old rider and elephant metaphor would have you believe.
Okay, let's take a breath. That was a huge amount of information. We've basically rebuilt the brain's decision-making flowchart from the ground up, based on the last decade of research.
We really have. We've gone from 2009 to, well, the very near future of 2026.
So let's synthesize this. Let's put a new map together for everyone listening. What are the key takeaways?
Okay, point one, the currency. We know for a fact that the brain converts wildly different good ripples as food, money, social reputation, moral virtues into a single universal scale of subjective value. The central hub for this is the VMPFC.
That's the head accountant. Cast 2.
Point two, the mechanism. The choice itself isn't a battle between good and evil parts of the brain. It's an evidence accumulation process, best described by the drift diffusion model. Different brain areas like the DLPFC just contribute different kinds of evidence to that process.
The stock chart model, not a battle, but a race.
Exactly. Point three, the big update. The ACC is not the decider weighing costs and benefits, it's the foreman. It comes online after the decision is made in the VMPFC to manage the translation of that choice into action.
Good space versus action space.
Okay.
A critical distinction.
Critical. Point four, the social brain. Kindness is a computation. It runs on the exact same hardware and uses the same common currency as selfish decisions. And we know the VMPFC is necessary for this. Without it, pro-social motivation fails.
And that computation is modulated by neurochemistry, dopamine, and serotonin.
Right. And finally, point five, control. It's not just the ancient brain driving us. The modern cortex, the OFC, provides top-down guidance to the striatum, actively directing our motivation towards our goals. The rider is steering the elephant.
So this brings us to the ultimate so what question. Why does knowing any of this matter when I'm standing in front of that vending machine tomorrow?
For me, it completely changes the narrative I tell myself about my own choices, especially my bad ones. When I choose the donut, I no longer frame it as a personal or moral failure. I don't think I'm weak or I have no self-control.
You see it as a computational outcome.
I see it as an evidence race that the fast sensory information happened to win, and that's empowering because it gives me a new way to solve the problem. The solution isn't to try harder or fight myself. The solution is to change the parameters of the computation.
To hack the drift diffusion model.
To hack the model. If I want to choose the apple next time, I need to find ways to boost the signal for the health evidence. Maybe I spend 10 seconds before I approach the machine consciously thinking about my health goals. That gives the slow evidence from the DLPFC a head start. I need to stack the deck in favor of the choice I want to make.
And what about on the social side? How does this change how we view other people's behavior?
I think it offers a pathway to a little more compassion. When we see someone act in a way that seems incredibly selfish, our first instinct is to label them as evil. But this research suggests another possibility. Maybe their brain's exchange rate is just different. Maybe their VMPFC, for reasons of genetics or environment or injury, just isn't efficiently converting social signals into value.
The hardware problem, not a character flaw.
It could be. And that doesn't excuse harmful behavior, but it changes how we might think about addressing it.
And we've established that this calculation is tuned by neurochemicals like serotonin.
Based on the Batten paper, absolutely.
So, if altruism is a tunable chemical calculation, couldn't we just tune it?
You're talking about pharmacological enhancement of morality.
I am. I mean, think about it. We're developing drugs that change the value calculation for food to treat obesity. They literally make food seem less rewarding. Could we develop a kindness pill, a drug that selectively modulates serotonin in the VMPFC to make you value the well-being of others just a little bit more?
Scientifically, based on the mechanisms we've discussed today, it's plausible, the pathways are there, but the ethical implications are staggering, and the door swings both ways.
What do you mean?
If you can develop a drug to make people kinder, you could also develop one to make soldiers more ruthless. Or what if a commonly prescribed antidepressant accidentally has the side effect of downregulating that system? Could we inadvertently engineer a less empathetic society?
If goodness is just a firing rate, then it's adjustable. And that is one of the most profound and unsettling ideas I've encountered in a long time. It feels like we're peering into the source code of what makes us human.
It does. And it puts a huge responsibility on us, not just as scientists, but as a society, to understand these systems, to understand that our choices, our virtues, our very characters are the output of a biological process, a process we need to protect.
We're all just sophisticated evidence accumulation machines. But we're machines that are built to care, as long as the math works out.
The math of kindness.
Thank you for listening to The Deep Dive. Go out there, stack the deck for your own decisions, and we'll see you next time.